Hello, ladies and gentlemen. Let's wait a second for more people and then we can start. Okay. I'm transmitting on news equipment, new computer, so if you have any issues with audio or something now let me know, I can adjust that. Okay. Great. Now there's only one person watching, but we will start in a moment. Okay, so let's start. Ladies and gentlemen, we welcome on our first lecture after a break. I finally am able to speak again, and hopefully I will be able to do it more longer. And today's lecture is a continuation of our previous lectures that were available to you through video with my edits, and we'll continue linear models. The topic of lecture 4, which will be probabilistic computation, will happen, but not today. I'm not sure when, but it will happen certainly in this next week or a bit later than that. Fortunately, it's not that important for us at this moment. However, I will keep the formula that was previously, that is the lecture that is joining both the slides and discussion of Jupyter notebooks, which are available to you since I think Sunday on the GitHub. So if someone was interested, could look at them. And we'll focus on linear models because linear models are the backbone of all statistical and mostly machine learning also approaches in practice of data analytics, because generally we always want to have to model some kind of relationships. We often don't know what those relationships are, and linear relationship is always the some kind of an approximation. If you remember from physics that sine function can be approximated with an angle of the sine of an angle can be approximated with an angle. If we consider it in radians, it was linearization. If you remember control theory, the backbone of the entire control theory is linearization, that all processes can be at least locally modeled by a linear process. So that's why linear models are important, and of course they can work also in the different approaches. In control, we had a complicated model that we were able to construct using laws of physics or laws of mass conservation or some other underlying knowledge, and then we could linearize that linear model. In case of statistics, we just assume that the linear model is at least locally good, and then we want to use it to approximate the relationship. And that's the idea of linear models in statistics, that we estimate the parameters of linear model and hopefully it will work. This approach also works in control. This is an approach of linearization by identification, that you just use one of the identification methods to fit a linear model to a non-linear process, but around certain equilibrium or set point. In such situation, then that model works and it can be useful. So, without further ado, let's go into linear models, because generally linear models are called maybe I'll just one more thing. Today's lecture is strongly based on the book of Richard McElrath, Statistical Rethinking, 2nd edition. We are using data from Richard McElrath's package, and we are considering the same examples. And also, this picture is also from this book, because this is generally the main idea that kinda explains what we are having with linear models. Because even in the ancient ages, in the age of Ptolemaios, there was a model of solar system created with the assumption initially that all the planets, stars are traversing the sky on circles, on circular orbits. And of course they don't. We know now they're on the ellipsoidal orbits. However, in those times, in order to compute that, they've seen that, okay, circular orbit does not work, so maybe epicyclical orbit works. What is an epicycle? Epicycle is that instead of movement on a circle, we move an additional circle on a circle. That is, when we have this big circle, the smaller circle moves around it with the point in the middle, and after that, and around this middle of the smaller circle, our object actually moves. So the middle of its revolution revolves on this one circle, and it's by itself moves on its own circle, something like an orbit, in a sense like an orbit of this second virtual circle. These are the epicycles. The idea was that introduction of epicycles actually improved the representation. So from the data analytical point of view, this model was very accurate. It allowed us to predict the movement of the planet regarding Earth, and it is it's also kind of nice. But we now know that planets do not revolve on the epicycles; they revolve on ellipsoidal orbits. So why this one worked? This one worked because actually it's a very naive Fourier series representation of a periodic orbit. Additional epicycles, because you can always add an additional epicycle, additional circle, which moves around this circle, which moves around this circle, and adding additional and additional with increased complication of computation, it's still it improves the computation quality. Why? Because it's in a sense representation of the movement as a Fourier series without using Fourier analysis. So this approach led to good results, but of course it does not represent the causal relationship of what we observe and what is factually going on. So we have a physical situation, we have a system that is revolving, the system of planets and stars in the universe, and the movement has its own underlying phenomena, which is not captured by our model. However, its numerical values, its predictions using our model are very good, or at least very accurate. And this is very often a case with statistical models, and with even more extent with machine learning models, because models are very good at predictions, but they do not represent the phenomena. The best example are of course neural networks, because all the processes that are realized using deep learning are not really representing the process. When we are using different machine learning methods like decision trees, we know that the phenomena is not a decision tree. We know what's going on, but the decision tree is a good predictor or a classifier in that case. So that we can use it because it has good quantitative information. It does not give us qualitative information. So we know we get the numbers right, we don't have a model that represents what's going on. So is that bad? No. For certain applications, it is very good. However, we need to be careful when making decisions based on that, because if we make decision of changing certain parameters, especially after, or variates outside of the known model, outside of our previous expertise, our model might lose sense, because in such situation it is not the it was never describing the causal relationship, and because we've got out of its comfort zone, it got also it started giving wrong predictions because it didn't have any base to predict right. This is a problem of generalization. And that's the general idea of creating a models that we know that are not really true, but are still useful. Because again, linear model, not really true, especially not in large scope. However, it can lead us to good predictions, and sometimes enough. Also, it can also be sometimes describe causal relationships, but this is a more advanced topic that probably we won't be covering in this course. So, generally, what we will be considering today is regression. At least what is called in statistics as regression, because our regression models are used to explain relationships between independent and dependent variables. So independent variables can be those things that we measure, and dependent variables are quantities that we are interested. For example, classical, we know the parameters of a wine, we want to predict its price. This is the classical regression model. However, what we really want is that we want to create models that are used to determine a numerical value. Those models, with careful analysis and good understanding of the process, can also be used to explain relationships in more fundamental way, but we need to know what's going on. We need to analyze it in the context of cause and effect and laws of physics and general logical relationships that must be covered in order for everything to work. So that's the main idea. Okay, and what we are really doing here will be general linear regression, which is based on the Gaussian distribution. Because generally we will be interested in models that are behaving in accordance with normal distribution. This is not the only case. We can use generalized normal distribution, for example, using student distribution, which you've seen in the example with the Newcomb experiment. However, generally we are focusing on the normal distribution, so we assume that y is normally distributed with mean mi and standard deviation sigma when it is a random variable from the distribution. And in our Bayesian context that we are covering during this course is that we are uncertain about an actual value of y, but our uncertainty can be described by a normal distribution. So we know that our measurement process relates the underlying relationship in a form of a normal distribution. That is normal distribution. There is some kind of mean value, and there is some kind of the uncertainty covering it that is covered by the standard deviation. So we have two parameters that give us the coverage of variable y, and generally we always want to find a description of our uncertainty about the problem, because knowing that we can make inferences or predictions with margins of safety that we can find, because in the situation of uncertainty we almost never are able to exactly predict the value of interest. We can, however, predict it with some kind of bounds. In simple cases, those bounds and value can be determined analytically. In more complicated situations, we can cover it by estimating the distribution of this measurement process, for example, using Monte Carlo simulation. And we want to find such description in one or another way in order to create this model. And statistical models are generally like robots or computer programs. Then they process data, but if data is bad, the results will be bad. If we we teach them bad, they will learn badly. And in case of Bayesian modeling, we kind of get the uncertainty about our data, about the process, encoded in our model. And we encode it with probability distributions, and that's why normal distribution is here popular, because of its many desirable mathematical properties and also certain relationships that make sense. Because generally Gaussian distributions are everywhere, and they are but they are not everywhere as much as we would think. Not every distribution we see is Gaussian, because they are often not. But very many processes behave Gaussian-like. First of all, we know from the central limit theorem that you should kind of remember from the probability course on the first year of your studies, is the that sum of identically distributed independent random variables is normally distributed. This abbreviation IED is independent identically distributed random variables. So if we have sum of those variables, it is normally distributed, which is very important, for example, in Monte Carlo computation, where we compute expectations, which gives us the central limit theorem as a power for Monte Carlo error estimation. But that will be covered on a lecture that should happen before, but that's a tangent. So let's start with a very simple thought experiment. Let's imagine us that we have a football field or any other sport field, and you get 1,000 people and tell them, those people, okay, you stand in the middle and then move randomly into any direction as long as you want. Let's say no more than 1 meter. So you will move, okay, you move along the line, and you just move either left or right randomly, and you move randomly with randomness. So generally you take a step with, mathematically speaking, of uniform distributed between -1 + 1 meter. So you just move this way. So how the positions of those people will behave after making those steps. So how they will walk around the field. And we can actually see that numerically, because by performing a very simple calculation, we can see that people will be covering more and more. Starting with the middle, they just move they move no more than 1 meter in each side, but because there's a lot of them, we can see how this behavior changes. And this distribution of those steps, because look at this, each of those steps, after some number of steps, we get the sum of identically distributed steps, because the length covered, or the position in this case, will be a sum of steps with positive or negative direction. So from the central limit theorem, they should be normally distributed. those positions of people. And this can be observed even after 4 steps, that we get some kind of bell-shaped curve. After 8 steps, even more visible. After 16 steps, we get a very nice curve that fits it very well. So generally, by observing such, for example, movements, we get the normal behavior. The sum of identically distributed steps leads us to this situation. Okay. So generally, the normal distribution is good for multiple things. So we have the processes that are a form of increments, which are very often happening. So we have an increments, those sums will be normally distributed. This is also true for a small percentage changes. So if we multiply by numbers close to 1, this behavior also is normal-like, but this comes from the linearization actually. And if you multiply by large numbers, we have a normality on logarithmic scale, because you get the log normal distribution, which is exactly that, normal distribution on log scale. So if you have repeated operations on the on a number, so we have series of steps that are covering the situation, either by multiplication or addition or combination. The result will be normal-like, at least on some scale. So it is very important. So it seems that this normal description is rather important in practice, especially that, for example, this comes again with errors and stuff like that. So I started recording by an accident. Okay, sorry. I've removed my camera by an accident. Hopefully I will be able to cut that. So okay, that was a interlude, a technical issue again. So of course, sorry. Okay. Fortunately, I'm recording this, so maybe I'll be able to cut it later and edit it, so it won't be that irritating for people watching that later. For live viewers, sorry. Generally, what we have here is that when we construct our model, we must focus on what are we doing here. First of all, we need to recognize the set of measurements that determine the outcome. So we need to determine what are our variables of interest, what is the outcome of interest, what we observed, what data we've collected. Then we define the likelihood, so the plausibility of individual observations. So how the uncertainty is present in this relationship. So in linear models, it is usually Gaussian relationship, because it gives us the ease of computation mostly, and also if we do not have any motivation of extreme values happening here, normal keeps us rather tight in the neighborhood of 2 sigma from the measurement. So this gives us a little bit of leeway. So then we want to recognize the measurements that we want to use to predict our outcome. So we need to split our variables into dependent and independent. Then we need to construct our likelihood, our predictive behavior, based on our predictor variables. So we define the predictors, and then we define what parametric relationship is between those predictors and the model's parameters. And when we have those model parameters selected, so for example weights of the linear combination, we choose the priors for the model parameters, and then we fit the model. So we have priors, and then we go to the and then we can move to the our relationship. And how to practically do it? We can use these we can create it using standard Bayesian formalism. And this formalism says us generally that each of the outcome measurements is normally distributed with respect to certain mean and certain standard deviation. Look at it, however, that those means corresponding to each outcome are also indexed. Why? Because they are related to the predictors. Each of those means is a function of predictors. So in our case, we have an intercept, which is a standard name in statistics for such behavior. So we have a constant parameter that is the described by our relationship. That generally gives us the average value when all the predictions are equal to 0, and beta parameters are the parameters corresponding to the predictors. Predictors, because you can more than one. You can have multiple. Then this can be a vector. B also can be a vector in a sense, or a matrix. Generally, what we have here is that outcome is normally distributed with, in this case, fixed sigma, with a mean that is a function of predictors. In case of linear models, it's a linear function of predictors. And in practical applications, we want to give some kind of priors for those parameters, and usually good priors are some kind of regularizing priors. If we don't have any base for relationships, because for example, if we know that there's a positive, we're sure that there's a positive relationship between predictor and the outcome, then we need to focus on how to express that in the prior. So the prior will leave us in the right place. However, if we don't have such information, then typical choices are normal distributions, which gives us generally that they limit our, let's call it, search space of parameters, that we are looking for parameters, but it adds them to the it makes it smoothly by generally limiting the probability of going more than 2 sigma away from the value. In case of prior for sigma, then we usually, of course, sigma has to be positive, so we need to use some kind of asymmetric distribution. And typical choices are either Jeffreys prior, which is our ignorance. Exponential prior is very good because it's a bit heavier tailed than Gaussian, but it's still rather light tailed and gives us the information. Or in case of, and we can also use half normal distribution, that to estimate to provide the prior for our sigma. So half normal is the lighter tailed distribution that is more focused around 0. In why we want something heavier, because we might want to be prepared to give a bigger standard deviation than initially expected. So we want to leave some probability available to sample there. So this is almost a classical linear regression. Why? Because classical linear regression is this part. This here, these two lines. In case of in classical linear regression, we have a normal distribution. However, what we have in the classical numerical is that all priors for those parameters are flat, and also sigma is not being estimated. So we just assume flat priors, so uniform distributions, no without any bounds, any number is okay, and then the solution for this system is, of course, standard pseudo-inverse matrix of the design matrix, or so-called the matrix of predictors. But in Bayesian formalism, we assign priors, so this can be very useful because thanks to that we can avoid the problems with the that can be with the for example, hard to identify models. Okay, so as I mentioned earlier, linear models are justified by Taylor expansion because locally any function can be expressed in a linear using only linear terms, and the problems is, of course, like generally the problem is with locality. The problem that is not always visible in in analyses given by the humanists, economists, and people like that, because in their behavior they sometimes forget about this locality requirement, and they just focus, oh, there's a threat. But if we move on the same scale, those linear relationships are justified. If we have any background knowledge that justifies linear relationship is justified. However, if we do not have, then constructing linear relationship between one and the other variable is unfortunately not very responsible. Okay, so let's move to an example. Our example here will be modeling of people's height and relationship of height and weight in people. So this is not something like extremely complicated. We will, however, focus at the data set obtained by Nancy Howell in the 60s, describing the behavior, the parameters of Kong people. Kong people are an interesting nomadic tribe, which is interesting because they were very isolated population. So using those isolated population, we have a lot of simplification when creating such models. Those we do not have the interactions from the other populations. So from anthropological point of view, they were very interesting. And this is a nice, simple, small data set of weights of anonymous people that we can use in order to create a simple model. So that's why we consider this one. Of course, different data sets are also okay, but this has given us at least a certain practical approach, because this is something that actual real anthropologists do when modeling. So we have the Kang people tribe measured in the 60s. We have a group of people. So let's do some modeling. Okay, so we move to Jupyter. Again, we have what we are really using here is the I have not pulled from the repository. Wait a second, because this is my bad, and I made a bad thing. I made a bad thing because I have the old code from the repository. My bad, sorry. I've checked everything except that. So there will be some more issues here. Okay. So let's see if it will work. Yes, it will work. Okay. Sorry for the delay. We go back to the modeling of Kang people heights, and in our case, what we did here is this is again an adapted code from the last year with certain changes. It is optimized for command stan. It uses my mini package of VDA tools that you can use if you want to. If you don't want to, there's no necessity for that. But it can be useful to some visualization. That's why it's living here. We are again with the ribbon plot function and of course we are using Arvis, NumPy, stats, pandas, stuff like that. Standard situation with Seaborn white style, so the pictures will look nicely, and with the appropriate DPI, so they will be larger. And this is the main idea. We are getting data online, so we are getting it from the Richard McElrath GitHub, and we are using pandas to get it, so we are just reading a CSV file from the web. And we focus at the moment, in order to preserve the locality, we'll focus on the adult part of the population. So we have our model that is the Kank people, consisting of smaller people between around 150 centimeters or less, and also more, with low body weights and their ages. So we are focusing on the adult population that don't have much fluctuation in their height, in order to analyze it. So this is filtered data set of around 300 people. So what we are doing here, we start with avoiding the linear regression at all, and let's just focus on the using of normal model. So let's get a normal model and get it working. So it's a special case of linear model with beta parameters fixed to 0. We will start with prior predictive checks, which you should be already familiar with. So we will assign priors for our parameters. We will then, using prior predictive distribution, so generally we will sample from the likelihood functions without any data. We will want to see what kind of data we are expecting from our prior distributions. We will compare it with real data, so we see that there is no dissonance between them. We want our prior to be much more broad than the actual data, but we want our prior to allow us to obtain the real data. So we have our model which we are compiling. At the moment, there is an issue with command stan, at least on Mac. I'm not sure this is on Windows or not. You can answer in chat if you observe it. If you have blank spaces in folder names, like here, then you have to compile it every time. It shouldn't happen, but I've replicated in onto Macs, so this is not something that should happen. So that's why I've made an issue for the command stan developers, and we'll see what will happen with that. And maybe it's a Mac issue, I'm not sure, but it makes stuff a little bit slower. However, I have it all run, so I won't be running the code now. Especially that at the moment I'm on an M1 computer, so without the Intel microprocessor, and from what I observed, for example, compilation is unrepresentatively fast. In case of the, for example, Intel processors, it was slower. But let's continue. What we have here is that we compile our model and we get samples from it. What we are sampling here, we are getting 1,000 samples from from our model without any warm-up. Why? Because it's on only generated quantities models. We have no parameters, so we are not doing actual Monte Carlo sampling. We are just using random number generators from Stan, which are more efficient in a way because they are written in C and not in Python. So, and we get our simulated values. So we are simulating the height and mean and standard deviation. So as you can see, we are sampling from the mean. Oh, maybe some discussion of prior selection. We are sampling from the mean in order to get the mean with the at least 20. We have, or let's say, we do not have any idea of height of Kank people without any knowledge. But average height of an adult person is around 178 centimeters. So at least adult male, and we are giving it a wide normal distribution, giving it a chance to get it between setting a standard deviation of 20 centimeters. So 99% of our 95% of our samples will be between 218 and 138. So this is a very wide distribution. In case of sigma, we have the kind of puzzling exponential distribution with a parameter 0.067, but this is actually the mean of exponential distribution is 1 over the parameters. So in our case, it will be almost 15. So let's say that we want to have our height to be at least 15 centimeters of spread for the normal distribution for the height to have a standard deviation of around 15 centimeters. This is our focus. So like that's a positive with average of 15 centimeters. So we sample from this distribution, we get those variables, and we can visualize them using the histograms. And what we are really doing here is those histograms are ordered, and we are overlaying them with our prior distributions. So for our mean, we have the spread of very wide spread between 130 and 230 centimeters. So we have a lot of samples here. Standard deviation is between 0 and 40 centimeters, so it gives us a lot of space, and simulated height locates us in, let's say, a reasonable, most of the samples is at least in a reasonable interval, because we didn't get any or very limited number of negative heights. I think there's a one sample here hidden somewhere, and we have not exceeded actual observed world record of height, which was 272 centimeters. We have exceeded, again, except the 1 or 2 samples. This is an issue of using unbounded distribution for bounded variables, that we can always get something not working, but we can filter it later. Also, these are only our priors. Our data will constrain that more in the middle, or at least around the actual value. So getting those parameters is not that terrible. So we can now use our data in order to get the posterior inference. And for our posterior inference, we will create on our new model height1fit, which now needs some data. This data is an information of number of data points and the array of n heights in centimeters. Our model parameters will be mi and sigma, because they will determine the relationship between heights and the measurement process. So we keep the priors, because in our previous observation priors are relatively reasonable, and we model estimate parameters mi and sigma, because heights are distributed as normal distribution for mi and sigma. And for each of those, we will generate a sample of height. So we'll get the distribution. We were not doing the tests like in Alvis proposed options. We just will generate for each of our samples of parameters. We will just generate one data point. So we won't be trying to replicate the original data set. We'll just for each of the samples, because it's not necessary in this case. So what are we doing here? We have our compiling our model, which compiles without errors. We provide it with the following data points. What requires mentioning here is that for all the arrays provided for command stan through command stan pi, from pandas we need to add the values attributes. So generally it takes our series or data frame slice and takes the data from it in the form of a NumPy array. In case of of PyStan, at least in the previous version, I haven't checked this PyStan 3, the values of heights are the values of data. You could send the slice of the data frame, and it was converted to appropriate option. In case of command stan, this is not possible. You have to use the NumPy array. So our sampling went relatively reasonable using the chains. We are not running diagnostics at this moment, and we get our summary using Avis. We limit ourselves only to mu and sigma parameters, using the stats flag to limit it only to the 94% confidence interval, which will, for clarity of the view, we've rounded up to 2. So what we've did here is we see here that mi has a very small standard deviation, is generally around 154 centimeters, but sigma of the entire process is between 7, 2 and 8. 2. So it is you have around 8 centimeters of uncertainty with some kind of asymmetric distribution. We can observe it using our joint posterior, so we can see how it behaves. So we get samples of mi and sigma, and those mi and sigma are distributed in this way that there's a tight interval of 1 centimeter on the, or 2 centimeters from 133 to 155 and 0.5. You have a, excuse me, you have the tight distribution here and a bit wider distribution in the scale of sigma of 1 centimeter, at least sigma of 1 centimeter. So we can now compare our observed height to the predicted height, and this is not terrible model. Let's be frank. It gets a bit underway. It doesn't get a spread as much because it's a bit lighter here. It gets outside of the spreads somewhere here. But generally, it's not a terrible model. But certainly, we can do better. We can do better. We want to do better. So we want to get our observed height versus the predicted height and see what's going on. So, how we can improve our model? And natural expansion of our model will be adding a predictor. And adding a predictor is a very simple task because we just want to include weight as our predictor of height, because it generally makes sense. Heavier people, like taller people, should be heavier than shorter people if they're in the same, let's say, body weight or BMI ratios, right? And in the case of young people, the population might be tending toward overly skinny, but not to have the obese people. So we should have those differences nicely covered by this situation. For the purpose of modeling, we will be using the centering. Why is that? Because we want to have some kind of easier interpretability of our parameters, and we want to have we just take our weights measurements and we remove the mean from that. So we will get the centered values of mean, so that weight of 0 corresponds to an average weight. Why is that useful? This is useful because it is easy to interpret that our intercept coefficient of our linear model so alpha coefficient, will be the average weight, average height for the people of average weight. So if people are average weight, the predictor takes a value of 0, and only this intercept corresponds to the entire relationship. So so alpha corresponds not to the 0 weight, because 0 weight makes no sense, but alpha corresponds to a mean at the average weight. So that's why centering is popular. It has certain limitations because it can get us to some pathologies in certain cases, but we won't be covering it today. So we want to do again a prior predictive checks. Why prior predictive checks are generally something that we should do always or almost always. I'm skipping it sometimes, but rarely, because this is the easiest way to check if our initial assumptions make any kind of sense. Because if our prior predictions do not allow the data to happen, our prior predictions are wrong. Or if our prior predictions are very well motivated, we should check our data. Because something is terribly wrong with data if it's absolutely inconsistent with one another. So it is a tool for checking for our own manual errors, our conceptual errors, and generally model specification. So this situation is very, very similar to the previous one. We have the normal distribution of parameters. We have the exponential distribution of uncertainty. And in our case, we change the guaranteed quantities in this way that we are sampling from our normal distribution n times, because for each data points, or actually for each predictor of weight, we are predicting the height of the height. So for each of weights, we get one height using our model. So we sample alpha from normal as previously. We assume that average person will have an average weight, and beta for beta we assign normal distribution from between 0 and 10. So model compiles without any issue. We are not using real data. We just provided 50 of samples that are equi-distributed between minimal and maximal observed weight. So of course, the standardized weight. Standardization will be in a moment. So we create an artificial data set for our artificial prior sampling. So we are not the data set, but a predictor set. We create an artificial predictor set that makes some kind of sense, because we want to just cover the entire predictor range. So we are getting the values and see what's going on. And we are not using data too much, because generally this is the problem with all the priors and posterior predictive checks, that there is certain kind of logical fallacy that you shouldn't use data in prior specification, because if you are in the prior specification, then your prior is a function of your data, and then you add the data, so using the same information twice, and you will get an overfit. But on the other hand, sometimes we only have that data and we have to use something to get some kind of regularization. So be aware, don't care that much. For this purpose, nothing bad happens. If you, however, would take data and you would fit from the data priors, and then again that would be wrong. But if you get, let's say observed range, for example, that's not a bad thing. So again, we are sampling, as always, 1000 samples. And we get our alpha and beta parameters, and we plot them. And what we really have the problem that getting this prior for beta is not necessarily reasonable. This, of course, is a plot returned to the original scale of weight. So we are not using centered weight here, but actual weight. What's the problem? Problem is that our model gets us too large values and certainly too small values, because it can get you very small negative values, and that makes no sense. So this prior for beta is not good. It allows us to get negative slopes, which is generally not that justified, and it's problematic. That's why we will change this prior. This is why we are doing predictive checks. This prior makes no sense. Let's correct it. And we've changed the prior from normal into log normal. Why? Because log normal is distributed on positive values, and this relationship generally can only be positive, and it makes sense to be a positive one. And we've added the sigma of 1, which in a very, very broad case says that we have our sigma corresponds to 1 degree of magnitude. But this is a very, let's say, rough approximation of what's going on. And again, we will do this the same. So we have our model, we just change the beta prior to be a log normal, and we get the our sampling as previously. And this situation is much better because generally results that we get fit well between 0 and max observed height in history, and we do not get those strange values of low weights resulting in absolutely high heights. So this is the this prior is certainly better for this application. So again, changing priors to keep data reasonable is a good idea. To get a prediction reasonable is a good idea. To leave it working. Okay. So let's use ribbon plot to see how our model works. And generally, those priors are too broad and they are located too high in practice. But we won't be correcting that here because our data are still within details, so they should be able to, especially that we have a lot of data points, they should be able to move our data points to the our mean towards the data points. So let's move to the posterior inference. How our model looks like? Again, very similar. We have only one predictor. We have the data of heights, we have a vector of weights, and we are using transformed parameters here. Why? Because it will be much easier to perform these multiplications here to get the means for each of the heights instead of doing this computation inside the model. It will be just more numerically efficient. So for each of samples of alpha and beta, we get the vector of mu, and this vector of mu is located where it should be. And after that, we can generate from our vector of mu, we can get our sigmas. This can also be vectorized, but you need to use unit vectors that you multiply sigma by, so you will get enough samples this way. Okay, so there's a model, we create a fit from that model, compilation works. This is something I've mentioned before, the error that repeats here. This is something for you to check in your free time. Change the number of samples and see what happens when you take that model and get it from in the form of getting it more or less data. Here we are giving it 150 data points. You can give more. I think there's around 300 of them, if I remember correctly. I'm not running it now, so it will be faster. Okay, we get our data fit dictionary. We get it from this data frame. We get right values, and we compute the number of rows. So we'll be able to get the number of data points. Okay. So we fit our model, we get our parameters, we generate the ARVIS summary for it, and how it looks like? Well, it gets us that the alpha is still very closely, its interval is very close because it gives this average of 150 free and with movement of 0.4 centimeters in one or another way. Beta is the beta, which is here, is the coefficients, and this generally says there's a kind of linear relationship between centered weight and height, and we have managed to reduce the uncertainty of our samples. Instead of around 8, we have now around 6. So it's not that terrible also, with also tighter standard deviation inside it. So if we get our samples, we can look at what are our means. Means here are linear models between weight and height. So for each of samples from me, we get one of the models. So you can see it's located in the center of data. And we can consider this uncertainty from this model by using the ribbon plot. And here we can see that this uncertainty is this uncertainty of our mean. So we just, instead of just getting those samples, we average it. So the assumption is that underlying phenomena that is captured by our model of weight-height relationship is somewhere here, which is its mean is the darker path, and this mean has our measurement process or height generated process. These random factors that are added will result in our measurement. So this is the distribution of the weight relationship on the mean of height distribution. So remember, this is not an actual prediction. This is the parameter of the distribution. This is distribution of me as a function of weight. If we want to do posterior predictive distribution, then we need to consider our model, and in this case we get we can see that we have a good coverage of actual data points. Not all of them are covered in this 90% interval, but the question is how much more is there outside. This of course is not a perfect model, but it gives us certain situations, because as you can see, the spread here is also visible. So it might be hard to capture something, especially that this is not a general spread for all heights, but it's more located here around this average weight. So it might not be capturable by a linear relationship. And if we can see, comparing the alpha and beta to our priors, we get them much more, get them very tight in order to see here. So if we want to focus, for example, on a selected weight and make predictions of how much such people will weigh, so we can just add it and compute the mean weight for the 50 kilogram range. But in the beginning, we've reduced our data set into the group of adults. But our data set considers also the measurements of the kids. So what can we do with that? We can extend our data set to get the entirety of it, and we can, in order to simplify the situation, we will standardize this data set. What does it mean? It's generally the same as centering, but you divide it by original standard deviation, which gives you easy interpretability of, in case of weight, that one value of parameter of 1 says us that the or in other words, it says that taking a value 1 standard deviation away from the mean results in the value of parameter. So generally it gives us you remove the units from your consideration. You just see that, okay, if our data is away from the original data set, then or from the original mean, then we can add we need to add the number of actual number of parameter, which will, now that we see that the parameter will correspond to the influence of such deviation. So we get new data set with our standard weight is generally relatively small, so around 1 of the models, and we can then use our previous model in order to compute the data. Because we standardize the weights, we will get different coefficient from beta. It will be larger. Previously it was not standardized, now it's larger by an order of magnitude than previously. As you can see here, here was beta around 1, now it's beta around 20. So, using that, we can see how our model moves, and we can see that we have a systematic problem with our model. This model with new parameters estimated cannot capture the behavior of small weight people, which are well below the standard deviation of the considered population, the mean of the population. So in here we have a spread of between -2 and 2 sigmas, and we can see what's going on with the height. So this behavior is certainly not linear, but it doesn't mean that we cannot use linear model to capture its behavior. It will be a linear model, however, with respect to parameters. The predictors are generally values of values from some kind of table, and they can be prepared a priori. So we can get weight, and for example we can add a square of weight, which might be advantageous because here evidently we get a curve here. So we can add it here, and we can do again prior predictive checks with our priors here for the second coefficients. For the second order coefficients, we are starting with a normal again, but with log normal for the first order, as previously. Excuse me. And our model, again, we can see how our priors behave. Prior predictive checks should be something that we do generally often, and because of that, we get our sampling. And this is something I have not to run, but I removed it later to here, and here it works, so there is no issue. Again, the problem is that our prior does not capture everything, but this is normal because the model is more complicated, and simulating data we get the parameters. So setting the actual model, we can now move to again, the change is generally very small. We just add the beta 2 parameter, and we are adding square of weights, which we compute using for loop in the transform parameters. We compile it, we generate data fit, and we predict the height using our model, and we predict the coefficients using our model. Using our model predictions, we can see that it can rather well capture the behavior, but this is generally quantitative modeling because there is no justification of a quadratic relationship, except that it fits. But the fact that something fits doesn't make it logical, or does not make it causal relationship. It just fits and might be used for further applications. So this is something that you need to be aware. Again, we need to get the parameters for it estimated. So here we've provided our dataset our model in Stan with weight, and we've computed the square of weights. However, this is not the most efficient way because we can compute the predictors earlier by so-called design metrics, adding square and third powers, for example, to our original datasets, and setting the design metric x as a proper part of our data frame, and in this case will be those last 3 columns. So we are providing it with our design matrix with 3 predictors, so the first, second, and third power of weight, which will fit in our model again with the same priors, with not any much issue, and sample from it directly using Stan, with assuming again that we have 3 predictors, again using the same as previously spread of values of weights. So using that, we can see that again fitting of third order model is also very possible. However, this time not complicated model creation as previously, but we just use the multiplication of beta parameters, which is now a vector, not a set of 3 parameters, so we get a vector of 3 parameters, and we multiply by a design matrix X, which we provided by from here. Okay, going further along, we can see how it all works and how it concludes. We get the parameters of all those power functions, and this is a start of creating design matrices, which is generally important in the context of all regression analysis, because we are generally seeing that our model, which is a function of predictors, and adding additional predictors, is generally the easiest way to do it is by changing the design matrix, so providing it with columns of certain parameters corresponding to me. Of course, the problem is that choose parameters. These are difficult problems. You can use some, for example, model selection algorithms to select which model is the best for our data set, using, for example, Pareto smooth importance sampling, which we mentioned in one of the video lectures. And generally, we can represent our results in the matrix notation, which should be known to you that our means are corresponding to the to the intercept and the linear combination of predictors, and with coefficients hidden in the vector beta. The X is a standard notation for design matrix. So generally, we can put more complications in the design matrix. Those are described in multiple books, for example, in Statistical Rethinking, or in both Gell-Mann books on regression, or in BDA, that really or in multiple courses on Coursera, you can use many functions of linear predictors and put them into your linear model. You can use the all kind of functions. You just put them, evaluate the values for your data set, the set of independent variables, and put them into the design matrix. We have used polynomials as an option. We are not talking interactions because it's a broad topic, and generally it means that it's the best working for binary variables. For linear variables, the justification might be sketchy, because generally, as a predictor, you add a multiplication of 2 predictors. And with a binary variable, that means that what will you do if the binary variable was present or not? For example, male, female. What would you do? And this is easy to interpret. If you have 2 continuous predictors, their multiplication is, you have to have good reason to put it as a predictor here, except that it works, because if it's something works, again, this might be an issue. But here we are focused on different kind of models, so we can see that it can be more complicated, because you can create your design matrix using, for example, B-spline functions. So you can get more complication in your model without limiting yourselves to the elementary functions. So what are B-splines? B-splines are so-called basis spline functions, which are defined by the knots, and generally this is a universal method of approximating functions, that we approximate function as a sum of functions that are 0 outside a certain interval. For example, in this case, it will be interval of 0 to 4, for which we have defined 4 basic cardinal basis functions that are representing our result. So those functions are limited to 0, and their combination will be on sum of multiple intervals. So we'll be adding those functions together wherever they exist. So if function is limited, for example, to 4 subintervals, if we have 10 intervals, we just move it around here, this situation. Excuse me for a moment, I need to have a quick break because of I think a courier has come to my home. Wait a second. Sorry for this unscheduled break. Hopefully it shouldn't happen again. It shouldn't happen now because they were supposed to be later, but you know the couriers. So, generally, spline functions are limited to certain intervals. They give you the smoothness up to a certain degree, so it doesn't have infinite number of derivatives like polynomials do. They have limited number of derivatives, and they are very easy to use in order to approximate the multiple kind of functions, at least up to a certain level of the precision and smoothness. Splines are defined by knots, so if you have 4 knots here, you can define those functions that are behaving here as a sum of those functions that you can generally. It means, in a sense, it means that all those splines are on each of the intervals of the consideration. You will have, the function can be represented as a third order polynomial. For example, if you are using polynomial spline basis, and it comes from this summing of those functions here. If you have third order base, so you have 4 functions adding to each, from 0 to third order adding to each other on each subinterval. Because all outside of those intervals, you don't have a situation of having more of them. And generally, we locate our knots in the area of interest. There are methods of choosing that, and as I said, the functions are non-zero on, for example, on 4 knots and 0 outside of them. So for each subinterval, you have only 4 functions working in each interval, and their sum is a third order polynomial. And on the edges, you need to repeat them, losing additionally differentiability. And what is very nice in this situation is that generally you are modeling the entire function, which is defined on the entire interval, as a sum of those base functions. But each of those base functions works on very limited scope of the entire function. So we have sparsity here. First parameters work on only one end of the interval, later parameters work in the middle, and like that. So this is very similar to regression, because B-splines are our predictor, can be considered as our predictors, because using them on the independent variable, you get the functions of this independent variable, and you can use them as elements of the design matrix. And the question is how to select knots. And you have there are multiple situations. If we have evenly distributed samples, not in the sense that you do not have these more samples for a certain point of an interval and less on the interval. For example, you have more samples for the uneven distribution would be like you have a lot of samples on the large values and very little on the small values. Then there's an uneven distribution. In case if you have everywhere the same, for example, you have multiple time series that you've measured on the fixed interval, uniform grid might be okay. If are not distributed statistically, in statistics, one of the popular options of modeling is locate knots at the quantiles of samples. So you just use the quantile distribution and give you more knots in the places where you have more data points. And splines are good because they can capture local behavior better. They can get the localized behavior. For example, a transition can be captured or fault can be captured. Design matrices are generally sparse because the columns of design matrix will be defined for the entire interval consideration, but they are represented only on limited. They are non-zero on limited aspects. So you get a sparse design matrix, which can be exploited if you have a large problem. You have a lot of data points. Then maybe it will be useful to use that sparsity in order to get faster matrix inverses and stuff like that. And splines are a special case of Gaussian processes, which hopefully we'll be able to say something later during this course. So generally, design matrix is constructed as a value of spline functions in all the data points we have, but of course, for most of them, they will be 0 because they are outside of the area. So this is a very easy design matrix, and because it's May, we can use the nice spring topic, which is actually one of the oldest data set that we have. We have the data set of over 1,000 years, because in Japan there is a tradition of viewing the blossoming of cherry trees, and it was recorded in multiple records for over thousands of years. So we have the oldest data set, we have a lot of samples, and we can observe. So they can be used to observe certain behavior, but again, it's an interesting data set because it's the oldest data set. It's the largest time scale span that we have available on the macro scale, and not or like on a human scale, not on the scale of universe. On universe, you can of course get the older data sets, but it's an astronomical problems, not practical ones from our point of view. Okay, so we have the second notebook, which, because the time is running out, I will just move quickly over. The changes here that we are just getting from SciPy interpolate, we are getting B-spline function, and from datetime we're getting datetime objects, B-spline object and datetime object, because they will be used to create design matrix and to convert dates to sensible values. In case of plotting, we get again data from McElrath's GitHub repository. As you can see, we have the minimal values year 800, maximal value is year 2015, so we have over 1,000 years of observations. We are interested in the day of the year. If this information was missing from our dataset, we are removing those points using the not-a-name method, and our star model looks like it's generally very simple, because we provide it with a Bayesian matrix, like in linear regression modeling, with measurements, number of measurements. In this case, number of basis function is generally number of columns in the design matrix. We have a parameters that will be a vector of parameters for each of basis functions, and we compute our transformed parameters vector in a vector way, multiplying the design matrix by the vector of parameters, and assigning appropriate priors. In this case, setting alpha for 100, so around, generally in between April and May, and with appropriate standard deviation, with broad coefficients for each of the beta, because generally we don't have any justification of giving any of the basis function more weight than others. In this case, is here, and we get the exponential distribution, so we get of sigma, so we get the uncertainty of average 1 day standard deviation. So we are not analyzing the prior predictive distribution here, especially that we have not much time. Rest is the same as always. We compile our model, and this is our basis function. We get the quantiles of our data points. As you can see, we have more data points later, we have less data points. Here we consider 15 nodes on the entire 1,000 year period, and we are assigning appropriate values appropriate values here. Okay, so this will be the basis function. Our value is of course day of the year. The day of the year that's of the value we are interested in is on which day of the year our cherries were blossoming. So we have less information on the older days, we have more information now, so here are the answers our basic function. So our denser. So this are the elements of our design matrix. As you can see, they are 0 outside of first few nuts for each of those. So we provide the data set from our spline matrix. We provide outputs of values of the day of the year, which was like, that's why we've limited to only to existing values, and we are sampling it with the with Stan. So we get values of our parameters. As you can see, the spreads are differing here. They are not necessarily very symmetric always, but you get those parameters. We are not plotting them because that would be a bit complicated, but we can again consider the mean regression. As you can see, this is a linear model which models a nonlinear function, so there is no issue with that. This mean regression, you get these spline functions. You have a ribbon plot of the mean. So we estimated the mean and we see how it looks like, and adding the uncertainty of it. So we have posterior predictive distribution. We have around the same mean. We have the uncertainty where the data points are located. And as you can see, our model works better, especially in the end. But of course, not all the samples are again captured. But the model also is very simple, so maybe there are some additional justification of modifying it. Okay, this is it for today regarding new content. Are there any questions for all the 4 people that are listening here, which I'm very grateful for hanging with me through this entire experience? Are there any questions? Okay, I'm assume that there are not any. However, there's one thing more which I can now switch to Polish at the moment to communicate to you. Proszę Państwa, dla ewentualnie zainteresowanych, jesteście teraz na tym ostatnim semestrze, znaczy na pierwszym semestrze Waszych studiów magisterskich i jest, proszę Państwa, możliwość odbycia czegoś, co się nazywa stażem asystenckim, jeżeli ktoś byłby zainteresowany. U nas w zespole mamy miejsce, moglibyśmy mieć miejsce dla takiej osoby. Idea polega na tym, że to są osoby, które realizują, prowadzą zajęcia, robią badania naukowe, dostają jakieś tam niezbyt duże wynagrodzenie. Tam ich zaangażowanie jest na poziomie do 60 godzin miesięcznie, więc nie jakoś szczególnie dużo. Natomiast no, może być to ciekawy temat, nie wiem, czy pod kątem rozwoju w pracy magisterskiej, czy zobaczenia, czy nas interesują na przykład studia doktoranckie, coś takiego. Jakby był ktoś zainteresowany, zapraszam. Wyślę jeszcze pewnie jakieś ogłoszenie na Teamsie, na czata. Dziękuję Państwu bardzo i życzę miłego dnia. Again, have a nice day. No questions, so other matters, ask me directly otherwise. Thank you very much and goodbye.